Hi everyone, this is a continuation of the short introduction to the different parts of chapter 12. So the first part was talking about alcohols, thiols, and ethers. So what I want to do now is just have a quick introduction on naming and identifying the structure of aldehydes and ketones. So what is going to link these two groups together is going to be it's going to be really important type of functional group, especially in biology, is going to be the carbonyl functional group. So carbonyl is basically just what I showed there. It's a carbon with a double bonded oxygen where that carbon's attached to two other things. So for this, actually I don't like the way this figure is shown. So what I'm going to do is scribble out those charges because they are not charged. They are partially charged. How do I know that? Take a look at the electronegativity of oxygen versus carbon. And so there's going to be a pull up of electron density toward that oxygen. And this is actually what's going to make carbonyl groups, when we finally get to, reactivity of them, this is the property that pulling electron density up onto the oxygen that's going to make them particularly reactive. So, now that we've introduced this idea of carbonyl, it sounds simple because it is, but I'm going to use that word a lot. But we have our carbonyl group, and then what we're going to do is divide that into two other categories. And there'll be a third one when we get later on, so that would be a carboxylic acid. But right now we're going to stick with two compounds that have fairly similar reactivity, and those are going to be aldehyde and ketone. So the major difference is, if we take a look at the structure, they both have a carbonyl group, but aldehydes only have one carbon coming off that center carbon. It doesn't have to be a methyl group that's like drawn right there. Could be as long as you want, as long as there's one carbon containing bond, and then the other one is left as a hydrogen, which you see in pink. Ketones, on the other hand, will have that carbonyl bonded to two carbon atoms. And so that's the major difference. It seems trivial, but we'll find out later in terms of reactivity, it plays a very large role. So how are we going to name these compounds? So we'll start with the simpler ones of aldehyde. So aldehydes, again, to remind ourselves, are compounds that have our carbonyl. One of that bonds to that carbonyl carbon is a hydrogen, and then the other one is some carbon-containing chain. Could be a methyl group, like I showed in the last slide. Could be as big as a protein, right? So we need to just keep in mind that it's some carbon-containing part of the molecule. So it does give us options in the book to use common names. Like I said, to keep things straightforward, we are only using IUPAC names. So it actually is going to make it a little bit easier to name these because of old common names. Instead of having the methyl, ethyl, propyl, butyl, right? It was form, acete, propion, butyr, right? We don't need more things to memorize. Let's stick with the way that all chemists, if you said it to anyone, they would understand. And it's as easy as replacing the E in the alkane name with the word al, or the suffix al. It's just getting a little bit, making sure you're keeping track of all versus al. One is an alcohol, so there's where the OL comes from, and then the aldehyde, that's where the al is coming from. So let's see if we can put that into practice. So this is what we have here. I've given you a couple of names with the common and the IUPAC name. So again, we if we had something that was one carbon, we know that would be methane. Replace that last E with al, and that's exactly what we have, methanal. That's the IUPAC name. Most people have probably heard this as formaldehyde, and so probably in high school you know what this smells like. It doesn't smell pleasant, right? Ethanal, propanal, butanal, we're still following the same naming convention that we've seen for now alkanes, alkenes, alkynes, alcohols, thiols, and ethers. Even though, actually not for us, not for ethers, but there is a similar pattern emerging, right? So let's start talking about naming aldehydes. So again, we're going to start off, basically, let's find out, what is our important functional group. the way we're going to figure that out is to figure out what's our longest chain first. So I got 1, 2, 3, 4, 5. That's my longest chain. My base is going to be pent. Now I got to figure out which functional group is going to take precedent, what basically changes that final name. Well, I have an aldehyde here. And we said in the last video, we're going to treat alkyl groups as like the lowest of the low. That's the last thing that we want to take in terms of precedent of naming a compound. What do I mean by precedent? I mean, what's going to change that final name? Because now we used to be a pentane. Well, now it will be pentanol, because I have that aldehyde group. You never need to put a number for an aldehyde group. And I'll show you what I mean in a second. Number for aldehyde group. Why? Because it always has to be at the end of a molecule, because there has to be an H attached to that carbon for it to become an aldehyde, so it absolutely has to be at the end, so we're not going to give it the number 1. However, I go and find out my next important functional group. H's never count as functional groups, so don't worry. I have my methyl. My methyl's on the 2-methylpentanal. And again, we want to make sure we're keeping straight with our naming. Hyphen between numbers and letters. No space, no hyphen between letters. So we go through step by step, just like what I did there. Find out our longest carbon chain. Replace the ending with -al. Figure out what my last constituent group. It's a methyl group. It's on the 2 position. So naming ketones. Again, just to remind ourselves what the structure looks like. There's my carbonyl again. But in this point, that center carbon of the carbonyl is now attached to 2 other carbons instead of 1 carbon and 1 H. So again, we're going to remove the vowel off of whatever our UPAC name were, methane, ethane, propane, butane, etc. And you replace it. It looks like 1, but it's -one is the way you're going to pronounce it, because it comes from the name ketone. So if we have something like 1, 2, 3 carbons, there's my propane. Take off the E, propanone. 1, 2, 3, 4, that's butane. I have a ketone though, butanone. Anything beyond butane or butanone, we're going to have to start indicating where those double bonds are. Because if we look at butanone, if I put the carbonyl oxygen there, it's actually just a mirror image of the original compound that's drawn here. So that's why we don't need to distinguish it with a number. But pentanone does need to be distinguished where that carbonyl oxygen is. Here we can see we have 1, 2, 3 pentanone. Doesn't matter because it comes from this side, 1, 2, 3. It's symmetrical. But imagine you could have a 2-pentanone, and it would be chemically distinct. So after butane, we're going to have to start numbering. And then we can also do it for cyclic compounds, but like I said, for us, we're going to leave cyclic naming to the wayside for this. As long as you're aware of it, the only time I'm going to have you, I want you to be aware of the names. I'm never going to ask you a question, at least so far, to name a cyclic compound. But there's not much difference to it, right? I see I have cyclohexane, right? I have a ketone attached to it, so it becomes cyclohexanone. That automatically dictates that that's number 1, 2, 3. So and I have a methyl group at that position. We're following the same rules. The only difference is you're adding cyclo to it. So let's go through some of these naming systems again. We're going to fall back again, starting the same way. Find our longest carbon chain. 1, 2, 3, 4, 5. We'll go that way. Makes it a little easier to see. Figure out which functional group is going to take precedent and change that the suffix of the name. Well, there's a ketone. How do I know it's a ketone? There's a carbon. There's a carbon. It's not an aldehyde. And like we said before, again, when we're dealing with alkyl groups, we're going to treat those as the least important in terms of determining the name. So if I got 1, 2, 3, 4, 5 carbons, I know I'm going to start with pentan, and I'm dealing with a ketone, so it'd be pentanone. It's at the 2 position, so it's 2-pentanone, and then I have a 1, 2, 3, 4 methyl. So 4-methyl 2-pentanone. And again, we could go slowly through the steps, so if you need to have a little bit more time, right, we find our longest chain, change the ending from E to -one. We have to indicate where that carbonyl oxygen is. It's on the 2 position. And then we're left with one more substituent group, which is a methyl group at the 4 position. So this is a quick exercise, so you might want to stop and pause the video and do it yourself, but figuring out things are aldehydes or ketones. Well, the first thing we need to look for is our carbonyl oxygen. And then we take a look at what's attached to that carbonyl carbon. In the first example, A, right, we see that we have at least one carbon and another carbon. Well, I'm done. Ketone. Take a look here. 1 carbon, 1 H, aldehyde. Again, 1 carbon, 1 H, aldehyde. I really don't care what the rest of the molecule looks like, as long as I'm sticking to that that carbonyl carbon and oxygen. Again, carbon, carbon, ketone. So it's as quick as that. Don't let that overwhelm you. Ketone, aldehyde, aldehyde, ketone. Oops, I skipped a slide. I already gave you the answer. So this is more for you. I've already done the example on it. I'm not going to take up any more of your time. So go through that again slowly. I have the answers here, what the names are, hexanone and butanone. Oh, sorry, we got to keep going because there's some other substituents. So I'm going to let you do that on your own. The steps to walk you through are there. And then what we'll do is we'll pick up at another lecture video talking about the reactions of all these molecules.